So here's a problem. There's a two-stage rocket, and it's going to be moving in the plane. So right now it's just a two-dimensional rocket. We'll get up to a three-dimensional rocket problem in a couple of sessions. And the three-dimensional problem, that's a good one. I'm looking forward to it. It's going to be good. But okay, there's a two-stage rocket. It's moving through the plane. Now initially the rocket is located at position 2, 1. All right, so we have our plane. We have our position 2, 1. And in the first stage, for every unit of fuel used, it moves 5 units in the x direction, so it moves over 5, and 11 units in the y direction, so it goes up quite a bit. So it's much better moving up than it is moving over. In the second stage, for every unit of fuel used, it will move only 2 units in the x direction and 5 units in the y direction. Now, what's our goal? So far, it's just assumptions. So our goal is to get the rocket to another point. So it's to get it to the point 1224. So that's probably not exactly 1224, but for the purposes of the class, let's pretend it is. Okay, so I want to get my rocket, which is currently located over here. So here's my rocket, ready to go, ready to blast off. We got to make it somewhat accurate. Okay, so it's going to blast off there. All right. And we wanted to get it to that point. So determine, if possible, how much fuel should be used in each stage. So the question becomes, okay, how does this relate to what we've learned? And so what have we learned? So the last time we were talking about vectors. And vectors are about change. So we can think about, okay, well, what's happening is that as the rocket is moving, it's changing. So what's happening in the first stage? Well, we move 5 units in the x direction, 11 units in the y direction. We can represent that as a vector. So in stage 1, what we get is that there's a vector, and we would denote it 5, 11. And so what this vector says is for every unit of fuel, this is the change you're going to experience. 5 in the first entry, 11 in the second entry. Stage 2 is a little bit different. It says what? Well, now we're going to move 2 units in the x direction and 5 units in the y direction. So in stage 2, the change is 2, 5. All right. So what are we trying to do? Well, we're trying to sort of do some combination. And now we're like, aha, this is vectors. They're really good with what's called linear combination. So linear combination means what? It means you scale and you add. And so we can think of it in the following way. We're going to have some amount, let's say A units of fuel in stage 1. And so the net change from stage 1 can be found by taking A times the vector 511. So this is the change which will happen if we use A units in stage 1. Then we're going to say, okay, in stage 2, there's some other amount of fuel. I'll call that B. That's what we don't know. And that's going to be 2, 5. Now, this will now represent the total amount of change, how far or how much that rocket moves, under the assumption that we use A units of fuel in stage 1 and B units of fuel in stage 2. And our goal is to get to a particular point. So what we want to do is we want to move from the point 2, 1 to the point 1224. So we want this to be equal to something. Now, what do we want it to be equal to? Well, it's not 1224, because we're not trying to figure out our location. We're trying to figure out our change. All right, so how much do we change if we go from 2, 1 to 1224? What's the answer? 1023. You look at the difference. You know, I start at 2 and I end at 12, so the difference here is 10. Start at 1, end at 24, the difference is 23. So all right, so what do we do to figure out A and B? Well, one way we can think about this is we can think about, all right, let's put it into components. So if we simplify the left-hand side, this becomes 5A plus 2b, and that's the first entry, and 11a plus 5b, that's the second entry, and we want that to be 1023. And so again, I'm grouping things up by components, putting it all together. And now we say, if I want two vectors to be the same, the components have to be the same. So it better be the case that 5a plus 2b is 10, and 11a plus 5b is 23. Okay, so we're now into our bread and butter. This is the type of stuff that we love to do. We've got two equations, and we've got two unknowns. So we have to solve. Now these are in fact our favorite kind of two equations and two unknowns, because they're both what are called linear. And there's lots of ways to solve it. If you're very fancy, you can do something called Cramer's rule. I'm not very fancy, so I usually don't do that. Something else you can do is sort of say, well, let me just solve for one variable, substitute into the other, and work from there. What I like to do, my favorite thing is say, let me see if I can cancel. So suppose for a second I want to cancel off the b's. Now to say I want to cancel means I'm going to take these two equations and combine them together. And before I do that, I say, well, let's do something so that what's in front of the b's is consistent. So I say, well, right now one of them has a 2, the other one has a 5. And I dislike fractions, so I'm going to do the following. I'm going to multiply the first equation by 5. It's the same equation, it's just been 5'd up. So 25a plus 10b equals 50. And the second equation I'm going to multiply by 2. So 22a plus 10b equals 46. Now, those are the same two equations. I've just done the silly thing of multiplying everything by the same constant. But of course it wasn't silly, because it wasn't just any constants. It was done with the plan. The plan is to get it so that the b's had the same things in front. And now that we do that, we can combine the two equations together by subtracting one equation from the other. So if we subtract the bottom equation from the top equation, 25a subtract 22a would give us what? 3a. 10b subtract 10b, 0. Ah, our favorite thing, 0. 50 subtract 46, 4. All right. So 3a has to be 4. So the answer here for a is that a better be 4/3. So we're going to use 4/3 units of fuel in stage 1. How do we get stage 2? We can do the exact same process, or we can substitute. It doesn't matter. It's just a matter of how do you feel. Well, let's do a substitution. So here we know what a is. Let's put it into the first equation. So we get 5 times 4/3 plus 2b equals 10. Now I don't like fractions, so I'm going to multiply everything by a 3. So if we do this, we'll get 20 plus 6b equals 30, because I multiplied everything by 3. 6b is going to equal 10, because I subtract 20 across. And so b is going to be 10 over 6, but that simplifies to 5 over 3. And therefore, in stage 2, we're going to use 5/3 units of fuel. So our combined amount of fuel is 3 total units of fuel. And that'll get us to just the right location. All right, good. Well, this is all about combining vectors. So we can add vectors, we can scale, and linear. It's great, wonderful. But you might be thinking to yourself, I'd like to do more. That's asking a lot. What's the other thing we want to do? Well, if we can add and we can scale, how about multiply? That sounds pretty good. Let's multiply vectors together. Why not? I mean, we can add numbers, we can scale numbers, we can multiply numbers. Okay, so let's think about it. Now, the natural first thing to think about is when we scaled each entry. When we added each entry. So when we multiply, why don't we just multiply each entry? It seems really good, right? Ah, it's beautiful. And there's a lot going for this. Let's just point out some of the pros. It's easy to do. It's easy to remember. And it's intuitive. And I can see there's more space here left. It's probably going to say it likes long walks on the beach, you know, enjoys a relaxing day at the spa. And, oh, whoop, no, it doesn't say that. It's useless. Doesn't work at all. Now, that's a really bold claim to say it's useless. So I want to explain what that means. So remember, we're talking about geometry. We're talking about space. And so when we talk about space, we want to make sure that whatever we use actually has a meaning in terms of space, and not just in terms of our coordinate system. See, the coordinate systems don't define your space, they describe your space. And if you change your coordinate system and it changes how things work, then what you have is not something that's geometrical. So if you think about it in the following way, suppose I have two vectors, and I've marked two vectors here, and I have two coordinates marked by marking what I call the axes. And if I look at these blue axes, what do they look like? Well, if I look at a vector here, well, it looks like I have something like a comma 0. So it looks like I move in what I would call the x direction. Over here, it looks like I have a vector 0 and b. And if we multiplied those entry-wise, we'd get a vector called 0, 0, which is a 0 vector, which means, you know, it doesn't do anything. But suppose I didn't use that coordinate system. Suppose I turn my coordinate system. So if I turn my coordinate system, it's not going on the axes, they're now off the axes. So what's happened? Well, this vector over here, I don't know, it looks like it's going something like a negative a. And this vector over here, it looks like it's doing something like b positive b for some non-zero numbers. And so if I were to follow the rule, I'd get ab and negative ab, and these things are not the same. The 0, 0 vector is not the same as ab times negative ab. Okay, so that's what we mean when we say we can't use it. Because whatever we use, it has to have a geometrical meaning. Now, you might think, all right, well, I guess there's no multiplication at all. But the good news is we've got 2 lectures about multiplying vectors. So yeah, it's coming. All right. So we're going to talk about our multiplication. And we're going to start with a particular rule. So because there's more than one type of multiplication, we're going to give them 2 different names. So we have the dot product. So the dot product is the one that uses a dot. Now here's the idea about the dot product. We still are going to multiply the terms together. So before you said, hey, let's multiply the terms term by term. Okay, all right. We're still going to do that. But now what we're going to do is instead of saying the results are going to be a new vector, we're going to say, forget about making a vector. We're going to make a number. So we're going to multiply the corresponding entries in the other components together, and we're going to add up the result, and the outcome is a number. So the dot product says take a vector, take another vector, take them together, do this rule, and out comes a number. All right. So there's some examples here. If you have a 3-dimensional vector, a, b, c, dot, d, e, f, you get a times d plus b times e plus c times f. I should say dot product works in any dimension you want. So you can do it in 2 dimensions, you can do it in 3 dimensions, you can do it in 27 dimensions, whatever dimension that you want to work with. Now, let's talk about this. Okay, we'll do an example. Compute the following dot products. Now, there's nothing written down here, so we'll need some examples. All right, so someone give us a vector.
7, 9, 12.
7, 9, 12. So you've chosen a 3rd dimension vector. Fantastic. Someone give us another vector. 1, 2, 3. Now notice that the first vector was 7, 9, 12. And the second person said 1, 2, 3. What did they do? They also gave us a vector that was 3-dimensional. So this is important. The dot product, you have to make sure that the vectors are compatible. They have to have the same number of entries. So you can't take a 2-dimensional vector times a three-dimensional vector. You've already cracked that code. Good for you. 1, 2, 3. You're giving me nice numbers. You're hoping that if you give me nice numbers, I'll give you nice numbers, maybe on the exam. Keep hoping. All right. Well, so here we go. 7 times 1? 7. All right. 9 times 2? 18. That's right. And 3 times 12? 36. And if you add 7 plus 18 plus 36, of course you get 61. That is correct. We have space. Let's do another one. Let's do something that's not three-dimensional. Okay. So we need another vector now. 5, 4? All right. 5, 4. Okay, so it looks like we've gone two-dimensional. All right. Dot. All right. 3, 2. Oh, wow. Okay. You're being nice to me. I appreciate that. All right. So, 5 times 3? 15. 4 times 2? 8. And 15 plus 8 is 23. All right. Well, okay. Let's do one more. I'll make something up really quick here. Let's suppose I'll go back to 3 dimensions. You might wonder, by the way, why we focus on 3 dimensions. It's just because it's a very convenient dimension to live in and to work in. In fact, spoiler alert, 3 dimensions is really important for our next session. So, for a very interesting reason, but that's for our next session. But it's also because we tend to work in a 3-dimensional environment. So we figure, all right, let's understand where we live. It's good to understand that. So you can have negatives for a vector. That's perfectly okay. So we'll put a negative in here. We'll put a 2. You can have exotic numbers like pi. And what if, suppose my second vector was something like t squared, sine of t, and e to the t? All right. Am I allowed to do that? I guess. That's a great answer. You know, oftentimes you say, well, nothing forbids it. I mean, a vector, you think of as really just sort of 3 entries. And we're going to be moving in the direction where we're actually going to say, you know, it's just 3 entries. We can make them anything we want, including possibly making them functions. And so, yeah, you are allowed to have more interesting things, the entries in your vectors. Okay, so what's our answer? Well, negative 1 times t squared, negative t squared. 2 times sine of t, that's 2 times sine of t. And pi times e of t, that's pi times e of t. And of course, when you simplify that, you get negative t squared plus 2 sine of t plus pi e of t. Okay, there you go. All right, and that's the answer. Now, you might be thinking to yourself, hey, should we study this? Because before, we saw that it wasn't so useful if we tried to put it back in as a vector. Now, here's the nice thing about the dot product. It has a lot going for it. It's still easy to do, and it's still easy to remember, but here's the really cool part. It's useful, which means it has a nice geometric meaning. Now, we're going to get into that, but first, let's talk about some of the basic properties. And these properties are very easy to establish if you just go through and think about what happens entry by entry. So one thing that's nice is it doesn't matter what order you do your multiplication. U dot v, v dot u, same thing. You're going to get the same answer. And essentially why that's true is if you think about what's happening, what we're doing is we're multiplying the entries and we're adding them up. So the dot product works in a nice way because addition and multiplication works in a nice way. All right, so u dot v is v dot u. We can also say, look, if I have a constant times the first vector, k times this vector u dot v, that's k times u dot v. All right, well, that's kind of what you'd expect. We can also, and this is a really cool one, this says you can distribute. So if I have a vector u, and I'm dotting it with the vectors v and w, then that gives us u dot v and u dot w. So we can do what's called foiling now, because foiling is distribution. All right. Well, that's good. If I take the 0 vector, dot any vector, I'm going to get 0. And that's easy to see because you're going to take 0 in the first vector. That's the 0 vector has all the 0 entries. So 0 times anything is 0. And if you add up a bunch of zeros, you still get 0. And the last thing here is that u dot u is the magnitude of u squared. Now this is why we're starting to sort of hint at a geometrical meaning when we say it's useful. So we want to verify the final property. Now this is not a very hard thing to verify. You just say, well, let's just pick a vector, and we're going to pick a generic vector. And not everything has to be 3D, but we'll just give an example in 3D. So here's our vector u. The vector u is a, b, c. Now last time we talked about the magnitude of a vector. So the magnitude of u would be the square root of a squared plus b squared plus c squared. So in other words, you know, it's like a distance from the start of the vector to the stop of the vector. So that's how you find the magnitude. All right. So what's the verification? Well, we do the computation. U dot u. That's the vector ABC dot with ABC. All right, now the rule for dot product. You multiply the first entries, add, okay, that's a squared, add, multiply the second entries, that's b squared, and you multiply the last entries, that's c squared. So you get a squared plus b squared plus c squared. And now we say, oh, wait a second, a squared plus b squared plus c squared, that's what's underneath that square root. And therefore, that's the magnitude of u squared. Okay, so that's the verification. Now, at first, this doesn't sound very compelling to say it has a lot of geometrical meaning. But hold on. Now we get to do some fun stuff. Now we're going to go to trigonometry. So, the good news is, you don't have to remember this fact, because I'm going to tell it to you. There's something called the law of cosines. And you can think of the law of cosines as a generalization of the Pythagorean theorem. In fact, if you think about the picture here, if you said, I have a triangle with sides A, B, and C, and theta is the angle between sides A and B. Well, suppose theta were 90 degrees. It was a right triangle. Well, it's not the case here, but suppose it were. Then you'd have a squared plus b squared equals c squared. And if you set theta equals 90 degrees in this equation, cosine of 90 is 0, that part goes away. So you get the a squared plus b squared equals c squared. So the law of cosine says, okay, suppose you don't have a right triangle, how do you correct? And the correction says, well, a squared plus b squared minus 2ab cosine theta is equal to c squared. All right. So what are we going to do? Well, we're going to take this triangle and say, let's think about it in terms of vectors. So I'm going to replace the side that's currently labeled as A. I'm going to think, well, that's really a vector called u. And the side that's B, that's a vector called v. And then there's this other side going between. And that vector, I claim, is u minus v. So in other words, this vector that corresponds to the side C is u minus v. Now, how can you convince yourself? Well, just think about what you can do. Suppose I start in the corner, and I want to end up at that point. We know one way to do it is to go along u. But I could also go along these two sides. So this side would be v. So the moral is, whatever this is, has to be the case that when I add v, I get u. Well, u minus v, if I add v, I'll get u. So it is correct. So that is u minus v. Now our goal is to find the length of the side labeled u minus v. In particular, I'm going to find the length of it squared. And we're going to do it using two different things. So let's see. What should we do? Well, let's use our new tool. Our new tool says if I want to find the length of the new side squared, we use a dot product. So the length of u minus v, quantity squared, is u minus v dot u minus v. Now, suppose this weren't a dot product. You saw u minus v times u minus v. What would you do? You'd FOIL. But now, what we're going to do is FOIL. And why can we FOIL? Because foiling uses distribution. And we have the ability to distribute. So we FOIL it out. So you get your u squared, well, that's u dot u. We're going to get a u dot v and a v dot u. But again, order doesn't matter. So I really have two of these u dot v's. And then we have, at the end, a v dot v. Okay, so what can we do? Well, what does u dot u become? The magnitude of u squared. Similarly, v dot v becomes the magnitude of v squared. And so we have that, lo and behold, there we go, sorry. The magnitude of this vector u minus v is the magnitude of u squared plus the magnitude of v squared minus 2 times this dot product. All right, so we used our nice fact. What we haven't used yet is the law of cosines. So now we apply the law of cosines, and we say, well, if I want to find this length, again, I just think about taking the magnitude of each of these sides, so that b would be the magnitude of v, a would be the magnitude of u, and c would be the magnitude of what we're looking for, and we apply the law of cosines. All right, so there's the law of cosines. The magnitude of u minus v, quantity squared, is the magnitude of u squared plus the magnitude of v squared minus 2 times the magnitude of u times the magnitude of v times cosine theta. Now the trained eye will notice something here. These are the same, the magnitude of u minus v squared. These magnitudes of u squareds are the same. These magnitude of v squareds are the same. And therefore, these last two pieces have to be the same. They have to equal each other. So what's the conclusion? The conclusion is that u dot v is equal to the magnitude of u times the magnitude of v times cosine of theta. Now what is theta? Theta is that angle that forms when you put the two vectors together at their starting points. Now what's the nice thing about this? The nice thing is this is purely geometrical. It doesn't rely at all on your components, because this is a length, this magnitude of u. This is a length, that magnitude of v. And theta is a geometrical measurement. And that's why we can say that the dot product is a useful thing. It has a nice application. All right. Well, let's try some examples. So, we have, again, u dot v is the magnitude of u, magnitude of v, cosine theta. And we could also solve for cosine theta. So cosine theta is u dot v over the magnitude of u times the magnitude of v. So this also says, hey, suppose I want to find theta. I can find theta via the dot product. Well, I can find cosine theta. And oftentimes we say, well, find cosine theta. The reason being, you may not have a calculator. You may be stuck on an island and be like, well, I only got coconuts, but I can find my cosine theta, no problem. So here we go. Here's this picture. And again, this just emphasizes our nice geometrical understanding. I have this vector u. It has length 3. I have this vector v. It has length root 2. And here's this angle 3/4 pi. What's u dot v? Well, we say, no problem. Apply the formula. So u dot v will be the magnitude of u, all right, I'll just write down the formula again, times the magnitude of v times cosine theta. Well, magnitude of u, that's given, that's 3. Magnitude of v, all right, that's square root of 2. And cosine theta, well, what's theta? Is theta 3 pi over 4? It's not 3 pi over 4. What have we done? Well, notice, how have we put u and v together? we've put u so that the end of u, or where we finish at u, is to start at v. But where is theta going to come from? We got to put the tails. As someone says, the tails have to touch. They're not touching right now. But that's okay. Here's what we can do, is we can take u and we can slide it along. So I could move u, so it's right here. And if I did that, then the angle between u and v would be this angle. So what is that angle? That's pi over 4. Yeah, so be careful. Be careful. Make sure you've got the right connection between the vectors. What is the cosine of pi over 4, by the way? Square root of 2 over 2. And if you look, square root of 2 times square root of 2 over 2 becomes 1. Then you have the 3, so our final answer is 3. All right. Well, find cosine theta, where theta is the angle between the vectors. And again, I have forgotten to write down what the vectors are, so we'll just take some suggestions. Okay, so we need some vectors. All right. What are some numbers? 4, 4, 4. We can mix up. We'll put in a 3 there. 4, 3, 4. Okay, I need some more numbers. 3, 4, 3. Not the most exciting numbers. Okay, but I asked for numbers, so I guess I will take the numbers I've been given. All right. Now, let's see what we get. So what's the rule? So if I'm looking for cosine theta, I use this variation. So we're going to take u dot v, 4, 3, 4, dot 3, 4, 3, divide by the magnitude, 4, 3, 4, and the magnitude of 3, 4, 3. Okay. Upstairs, well, 12, that's 4 times 3, plus 12, that's 3 times 4, plus 12, all right. Downstairs, we're going to get 2 square roots. 16 plus 9 plus 16, all right. And then over here, 9 plus 16 plus 9. And we can clean it up. Upstairs, that's 36. Downstairs, well, 16 plus 9 is, of course, 41. That is the correct answer. And 9 plus 16 plus 9 is, of course, 34. Oh, well, someone's good. That's right. And the next step is, all right, stop. Okay. Because that's the answer. Okay, cosine theta is equal to that expression. Now, you might say, couldn't we go further? No. No, we stop here. We're happy with this answer. If you had a calculator, you could actually get a decimal approximation. You could take the arc cosine, and life would be good. All right, so we can find angles. Now, what's a nice angle? Well, is there a particularly nice angle for the cosine function? And of course, when we think of nice numbers, our favorite number is 0. Is there a nice angle for cosine? Pi over 2. Pi over 2. That, yes, that is a very nice angle. So, if I have that nice pi over 2 angle, what happens to the dot product? It's 0, right? Because I'm going to get the magnitude of u, magnitude of v, times 0. And it doesn't matter how big the magnitude of u is. It doesn't matter how big magnitude of v is. It's really hard to compensate when you multiply it by 0. So u dot v is 0. So now we have this really cool fact. If two things are at a right angle to each other, which we sometimes call orthogonal or perpendicular, if we want to have a hard time spelling, then it's the case that their dot product is 0. And so that's what we're going to say. We say two things are orthogonal if their dot product is 0. All right. Well, what's the use of that? Well, we can actually do the opposite. So sometimes we want to check, are two things perpendicular, or we might have some knowledge, oh, these two things happen to be perpendicular, what that tells us is it gives us information about their dot product, or we can use the dot product to verify that something is true. All right, so find out all values A, and to avoid more of the 3, 4, 3 phenomenon, I'm going to actually pick this time. So find all values A so that A, comma, 1, comma, 2, and 3, comma, A squared, comma, negative 4 are perpendicular. These were not chosen to be good. I'm probably going to regret my choice in a moment here. Okay, but here I have two vectors, but they're not quite fully defined. I want a number. And so there's some choice for A, maybe more than one, hopefully at least one, where these would be perpendicular. So if I want them to be perpendicular, what needs to be true? Dot product has to be 0. So 0 had better be equal to A1, 2 dot 3, comma, A squared, comma, negative 4. All right, so we carry out the dot product. A times 3, that's A times 3, also known as 3A. 1 times A squared, that's A squared. And 2 times negative 4 is negative 8. Now, that's, well, it's kind of like a quadratic because it is a quadratic. If we rewrite it, it's a little easier to see. A squared plus 3A minus 8. Now, if we were lucky, this would factor. I don't think we're lucky this time. But what can we do? Yeah, we can use a formula for it. You know, at least once or twice in the semester we should use the quadratic formula. So A is equal to the coefficient in front of this term. So negative 3 plus or minus the square root, our 3-term squared, 9, minus 4 times 1 times negative 8, all over 2, and that would be negative 3 plus or minus, let's see, we'll get 9. The minus 4 times minus 8 would be plus 32, and 9 plus 32 is a number, well, square root of 41. Again, that's all right. And there you go. There are two possible choices for A that would make it perpendicular. Normally, of course, we'll plan well in advance, and we're going to choose not just random numbers, but good numbers. All right. Well, what else can we do with the dot product? Well, there's a really nice thing we can do, which is the following. We can do what's called projection. So projection says, suppose I have the following scenario. I have this vector, and here we go. I'm going to label this as the vector that's called U. So there's this vector here sitting up somewhere. And now what I want to think about doing is I want to say how much of U is parallel to V. So here's this other vector downstairs. This other vector downstairs is V. So this long V. And so the way I can think about it is I can think about as this, I have really bright light that's shining, and I'm casting a shadow. So I'm looking and I'm casting the shadow down here onto the vector. So that what you get is you get this little piece here. And this piece here is the answer to the question. We call it the projection of the vector U onto the vector V. It's how much of U is parallel to V. Now, I oftentimes will just simplify and say how much of U points in the direction of V, but it could be the case that you might have a situation where you might have it where here is your vector V, and over here, this is your vector U, and if you shine your shadow, it'll actually point in a sort of a 180 away from the direction of V. So that's why we say parallel. It could be that situation. All right, well, so suppose this is what's true. my goal here is I want to say, what is that vector? How much of the vector u points in the direction of v? And this is a good thing to be able to answer because it's sort of trying to help us understand how useful something is. I sort of like to give an analogy. Now, something that can happen if you're driving a car, and you can tell this is a picture of a car because it says the word car. And in winters, it might happen that you get stuck. But of course, you're surrounded by Iowans, and so we're going to help you out. And all of a sudden, a wild flock of Iowans appear, and they're going to start pushing you. And there's so many, they can't all fit behind the car. So some people have to start pushing from the sides. Now the question is, who's actually being very useful? And the answer is people from the back. What about the people from the sides? They're helping a little bit, but they're not helping as much as they could. What's happening is some of their effort is going to move you forward, but some of it is not. So the projection, that's really saying how much of their effort is pushing that car forward. That's the kind of thing that projection is answering. All right, so we're after a vector. We're after this vector called the projection. Now, how do you find a vector? And the answer is you always think about the two pieces. Every vector always has two parts. The direction of the vector, the length of the vector. And if you understand those two parts, if you can answer those two parts about a vector, you have the vector. You're done. So the two things we have to figure out is the direction and the magnitude. Now the direction is really easy because the direction says, look, I want to end up being parallel to v. So the right direction to pick is the direction of v. And the way we do direction is by unit vectors. So that's why you see this 1 over the magnitude of v. So 1 over the magnitude of v times v, that's the unit vector that points in v. So that's how we capture that direction. Now the magnitude is maybe a little bit more subtle, but not that much. So think about what's going on here. I have this vector v, I have this vector u, and I can think about there's an angle between the vectors called theta. The theta that we've been talking about so far. And if I'm looking for the projection, then it's like I were to drop down a right triangle and I wanted to measure that length of that side. Well, in terms of right triangles, that's my adjacent side. And I can say that the length of the hypotenuse is the magnitude of u. So this adjacent side is the length of the hypotenuse times cosine theta. That's how the cosine function works. So that's the right length. And the nice thing is you might say, well, what about this backwards thing? Well, the direction changes sign, but the cosine will also be negative, so it all works out. It's beautiful. It's math is just set up to be so nice. So now that you have your magnitude and direction, you just put it together. So if you have the magnitude and the direction, you multiply them out. So length times direction. So now we just do a little bit of manipulation. All right. So I have the magnitude of u cosine theta over the magnitude of v. Now, we think and we say, boy, we saw something with cosine theta before, and we already have the magnitude of u. If we just had a little bit more, we'd be good to go. That little bit more that we're after is that magnitude of v. And so we just put it in there. But of course, we can't just put it in the top. That would change the expression. So we put it both upstairs and downstairs, which is why you now have a magnitude of v squared. And what do we see in the top? Magnitude of u, magnitude of v, cosine theta. That's the dot product. That's u dot v. And downstairs, we have magnitude of v squared. That's v dot v. And there you go. It's a beautiful expression. It's u dot v over v dot v times v. Now, one thing to be careful about is it's very tempting to look at this and say, hey, u dot v over v dot v times v, couldn't we just like cancel some v's out and it's like, hey, it's just u again? And the answer is no, it doesn't work that way. it's not like you can take 16 over 64 and cancel the 6's and get 1/4. That doesn't work that way. All right? Don't do it. Oh, wait, that's a bad example. Never mind. Okay. But the point here is, don't yield to the temptation to think, oh, these things cancel out. They don't do that. So be careful. Be careful. All right. Now, the last sort of note here is we said we found the part that's parallel to V. What if I want to find the other part, that perpendicular part? So in other words, if you were to think about it, let's put this picture back up here for a second. I can say you have U and V, and you can say, look, there's a piece down here. This is the part that points in the direction of V, but then there's this other piece right there that goes, and that's perpendicular. And how can you find that? And the answer is, well, once you know the parallel part, you just subtract that off, and that gives you the perpendicular part. So you have, lo and behold, I can find the thing that's parallel to V, and I can find the thing that's perpendicular to V. And so the projection is the parallel, you subtract the projection is perpendicular, and you can convince yourself if you add these together, you get back to U. All right, well, we have time for one more example. Okay, so quick, give me some vectors. I heard 5, and I heard a 2, and a 3. Another one. 4. Let's throw some negatives in here. -1, -3. All right, so here we have these two vectors, and we want to find the projection and the perpendicular part. Well, so the projection, not so bad. So projection of U onto V. So that's, all right, the formula, U dot V over V dot V times V. So we can do it. U dot V, so that's 20 minus 2 minus 9 over V dot V, 16 plus 1 plus 9 times V, 4, -1, -3. So 20 minus 2 minus 9, that's 9. 16 plus 1 plus 9, that's a number, yep, 26. And 4, -1, -3. So there's the projection. And if we want to find the other part, the perpendicular part, well, we take the vector U and we subtract the projection. And, well, okay, what do we get? Well, we could multiply this out. I don't think you gain much by multiplying it out. And the other part, 5, 2, 3, subtract 9 over 26, 4, -1, -3, and that is the answer. You could simplify it. Well, we don't learn much by simplifying. So, all right, well, So next example. Suppose that we're given that W is the projection of U onto V. Then what is the projection of W onto V? And why? Well, let's think about the picture here. So here we go. We have a couple of vectors. So I'll draw V, and we'll draw U. And so if we're looking for the projection of U onto V, well, we draw a line down, straight down, right angle, and we're going the same direction as V, but now the length of that side. This is W. All right, so there's W. So now the question becomes, what happens if we project the vector W onto V? So when we projected U onto V, we got W. And if we project W onto V, what will we get? Well, of course, the answer is if we project W onto V, we're going to get triple U. Yes? Right? Because we started with U, then we had W, so it's triple U. No, that's not. What is it? Well, what do we need? We need to have that the projection is going to go on to V. Well, notice, where does W and V point? See, W and V are parallel. So if W and V are parallel, then if I project, then what happens is I already have the right direction, and so that says that the projection keeps the same. So the projection does not change your vector. All right. And so in particular, we get that the answer, no, it's not triple U, it's just W. It's just W. Now, could we see that from the formula? Well, let's take a look at the formula. So the projection of W onto V is equal to W dot V over V dot V times V. Now, what do we know? W and V point in the same direction. So the angle between W and V is either 0 or it's possible that it's 180. So what do we end up with? Let's assume it's 0, just for simplicity. So what we get is that W dot V, since the angle is 0, that's the magnitude of W times magnitude of V. V dot V, it's magnitude of V times magnitude of V, magnitude of V squared times V. Those cancel. And now what do? Well, this is magnitude of W times 1 over magnitude of V times V. And oops, I'm forgetting all my little arrows. Little arrows, little arrows, little arrows. Okay. And what do we get? See, this is the direction of V. But the direction of V is the same direction as W, but it's the length of W, and therefore, direction of W, length of W, says that the output is in fact, yes, it's W. Okay. All right. So we can project. In fact, you can sort of do a sequence of projections, if you will. Now, the next little piece. In physics, we have that work is the product of force and distance. So work equals force times distance. Now, when we go to higher dimensions, we can still talk about force, but now what does the force have? Well, there's a direction of force, there's a magnitude of force. So now, force is not a number, it's going to be a vector. So notice it's a bold F. Sometimes you use an arrow to represent a vector, sometimes you indicate it with a bold F, and sometimes you just forget, but you say it's a vector. So context is important. Now what about distance? Well, because distance is a number. Well, that becomes a vector, but now what we do is we call it displacement. So displacement is, how much did you change? Well, that's a vector. All right? So now, what does the formula for work become? So remember, work was force times distance. And the question is, what's the right formula now? Well, think of the picture. Here we go. We have our force vector, and then what we do is we have our displacement vector. Maybe it's going in this way. So force, that's how much force was applied. The displacement, well, that's how much something moved. So the question is, well, what is the work? Well, let's think about it. Let's think about it. What we can do is we can say, well, how much of force is actually being applied to move things in the right direction? Because sometimes not everything works equally well. So to figure that out, we say, okay, let's do our projection. So I want to say that this part right here, that's the force that's actually being useful. All right, well, how do we do that? Well, if this is our angle theta, then what we have is that the amount of force going in the correct direction is the magnitude of F times cosine theta. Now that's not a vector, that's the length of that vector. And so now we have the force, and it's going in the right direction. So once you have that, you say, okay, that's how much force gets applied. the length of d is how much you will end up moving it. So that if we think of this as a one-dimensional, back to where we were, we can say, using the old formula, that work is the amount of force that actually is useful, magnitude of F cosine theta, and then the amount of distance you move. That's the total displacement, the total length. That's the magnitude of d. Now if you stare at this, you say, oh, well that's the magnitude of F times the magnitude of d times cosine theta. We're like, wow, that looks kind of familiar. We have a vector and another vector, their magnitudes, and theta is the angle between them. Take the cosine. What is that? Well, the answer is that's the dot product. So work is F dot d, the force vector dot displacement vector. And so it's kind of nice. So we went, the old formula was work equals force times distance, and the new formula, work equals force dot distance. Wow, what a difference. What a difference. All right, good.